Hello and welcome to another WJEC A level physics question. This was question 3 on the June 2015 Unit 4 paper. This is an internal energy, first law of thermodynamics type question, which nowadays fits into Unit 3. So what we've got is a heat engine, and it's got a cylinder with a leak-proof piston containing 2 moles of ideal gas. So that number of moles is going to stay constant. It's taken through a cycle from A to B to C to D to A as shown in the diagram, where we've got various pressures and volumes. And we've got to complete the table to show the temperature and the internal energy of the gas in state C. So we've got pressures, we've got volumes, we've got temperatures, we know a number of moles, so we can simply rearrange PV equals nRT to give T as PV over nR. So the pressure was 1.1, I think it was. Yeah, 1.1 times 10 to the 5. Volume 0.042. N is 2 and 8.31 for the molar gas constant. And that gives us an answer of 277.98. So going to the same number of figures that we've got in the question, that's going to be 278.0. To find the internal energy, well, we've got various formulas, U equals 3 over 2 nRT and so forth. But if we realise, well, let's write that down for a second. If we realise that nRT is equal to PV, a quick way of doing this is to simply do 3 over 2 PV. So we don't have any rounding errors coming from maybe miscalculating the temperature in the previous bit. So 3 over 2 times 1.1 times 10 to the 5 times 0.042. So once we put that into the question, we end up with 6,930. That's joules for the internal energy. Okay, the question continues by asking us to determine the work done by the gas for each of the following. Now, your general formula for work done by a gas is pressure times change in volume, or you can use area underneath the lines on the PV diagrams like we got here. So you can see for both section A to B and for sections C to D, there's no areas underneath the lines, and therefore there's no change in volume, and therefore there's no work done. So for both A to B and C to D, we can fill in 0 joules. From B to C, we're going to use pressure times change in volume, which is exactly the same as finding the area underneath the line. So we're going to multiply 1.1 times 10 to the 5 by the difference in volume here of 0.006. And that will give us 660 joules. Now we've got to be careful with signs. When gases expand, work is done, and therefore W is positive. But when gases are compressed, as we've got here from B to C, then the work is negative. So we're going to put a minus sign in front of here. Similarly for D to A, we're going to do pressure times change in volume. This time the pressure is 1.28 times 10 to the 5. And there's still the same change in volume of 0.006. And that will give us 768 joules, and it will be a plus 768 joules. To find the work done for the whole cycle, we can either find the area of the loop, so we could find the area of this rectangle, or we can simply add up the different work done that we've got. So we've got 0 minus 660 plus 0 plus 768, which will give us a net amount of work done of plus 168 joules. For the next part of the question, we've got to determine the cycles, or the stages of the cycle rather, in which heat is absorbed by or supplied to the gas. And we've got to show that the total amount of heat absorbed in those cycles, those stages of the cycle, is about 3,000 joules. And hint to use the first law of thermodynamics. Now in the data book, the first law is given as delta U equals Q minus W, but most of the time we end up using it in the form Q equals delta U plus W. So what we've got to look for is a change of internal energy plus the work done, and we're looking for stages where that will give us a positive answer. So if we look at the stage A to B, well, work done was 0, and we've got a negative change of internal energy, so it's not going to be A to B. B to C was a negative amount of work done, and there was a negative change of internal energy, so A to B and B to C are both not acceptable. For C to D, there is an increase in internal energy and no work done. So for C to D, we can find Q by using the formula. So let's look at CD. Q for CD is delta U, the difference between 6930 and 8065. And the work done was 0. So let's just do that on a calculator to make sure we get that right. So we end up with 1135 joules. For D to A, the final stage of the cycle, there's again an increase of internal energy and there was positive amount of work done. So the change of internal energy is going to be the difference between 9217 and 8065. Plus the work done, which was 768. And again, let's do that on a calculator to make sure we get that right. That gives us 1920 joules. So the total Q is just the 1135 plus the 1920, giving us 3055 joules, which is near enough the 3000 joules that we're asked to show. The last part is a formula that's not actually in the spec, but you just simply got to put some numbers into it. It's a formula that allows us to calculate the efficiency of this heat engine. It's the net work done by the engine, which was plus 168 joules, divided by the heat absorbed by the engine, our answer is 3055, with a multiplying factor of 100 to turn this into a percentage. Put those into a calculator and we get near enough 5.5%. Thank you very much for listening. Please remember to like and subscribe and feel free to add any comments below the video. Goodbye.